The Phanerozoic eon is the fourth and final eon in Earth's geologic history, and it is made up of three eras, the Paleozoic, Mesozoic, and Cenozoic. And the Paleozoic era is composed of 7 smaller periods, of which the Cambrian and Ordovician are the oldest. The Cambrian period is noteworthy in that during that time, Earth saw a huge increase in the abundance and diversity of different animal life forms. And so rocks of Cambrian age, much like here in the Western Grand Canyon and National Canyon, you see rocks of Cambrian age on a hike there, and they have fossils in them of various types and various abundances. In fact, in National Canyon, that's the shallow marine Muav limestone, where back in the Cambrian you might have seen trilobites like this, a very common arthropod that was present during the Cambrian, scurrying around on the ocean floor amongst these sponge-like archaeocyathids. So the appearance of life on a global scale in these shallow marine environments is something new for Earth, totally different than the preceding Proterozoic eon. So the Cambrian and Ordovician signal the beginning of this change. Let's begin with the Phanerozoic eon, which has a range of 541 to 0. Notice the 541, not an even number. We've discussed this previously. And now that we're in the later stages of Earth's history, the fossils in the rock record and various datable geologic units allow us to bracket the ages of these different time periods. And so that's why we get these odd numbered boundary ages like 541 instead of, say, 500. Okay, and so 541 to 0 is the Phanerozoic eon. You can say we're living right now in the Phanerozoic. Again, Phaner means to see, it's visible, and zoic means life. And the reason why we call it Phanerozoic is we can see life in the rock record. This is a timeline of Earth's history, specifically for the Grand Canyon, but it begins on the left with the Hadean, and then the Archean and Proterozoic, the 3 previous eons. Now finally the Phanerozoic here in the last 500 million years. You can see the Phanerozoic is about the same length and time as the Hadean, but much shorter than the Archean and Proterozoic. This timeline is to scale. The Phanerozoic is the last of these 4 eons, and it's composed of 3 smaller eras. And you can see them here, the Paleozoic, Mesozoic, and Cenozoic. Each get successively shorter, and the Cenozoic is much shorter than the other 2. The Paleozoic era stretches from 541 to 252. And on this time scale, which is again for the Grand Canyon, this is just the Phanerozoic part of the Grand Canyon's history. And so it starts with the beginning of the Phanerozoic here and the end on the right. So the Paleozoic, Mesozoic, and Cenozoic are the 3 eras. You can see the Paleozoic in blue stretches from 541 down to 252. And it's composed of 7 periods. Okay, these smaller units of time include the Cambrian and Ordovician, Silurian and Devonian, Mississippian, Pennsylvanian, and Permian. The Cambrian period stretches from 541 to 485. So here is the official geologic timescale from the ICS, the 2018 version 8. And the Cambrian is right here. It's the oldest of the Paleozoic periods. So you can see the time there, 541.0, plus or minus 1 million years. That means that that boundary has been dated by a volcanic ash or something like that, correlated probably with some kind of distinctive fossil assemblage at 541.0, plus or minus 1, which means it could be as old as 542 or as young as 540. 1 million years of error there is pretty good. Okay, and so 541 is the beginning of the Phanerozoic, the beginning of the Paleozoic, the beginning of the Cambrian. And it stretches all the way up to 485.4. For the rest of the course, I'm not going to be referencing the error numbers on these because they're all pretty good in terms of precision, but 485 or so, I'll just round it, and that is the length of the Cambrian. The Cambrian itself is named for an area in England called Wales. It's in Western England, and when people were traipsing around the country trying to figure out the geology and give these rocks an age, they said, well, we're in Cambria, let's just say they are Cambrian in age. And thus, rocks that they saw underneath these Cambrian rocks they called Precambrian. This time period stretches across a few tens of millions of years and can be described in terms of early, middle, and late. It's fairly common that we do this with time units, subdividing into an early or middle or late section. So early Cambrian, middle Cambrian, late Cambrian, that's fairly common. These other names you see here, we won't be referencing so much unless there's a reason to. And as you go to the right on this time scale, you're getting into smaller and smaller, more detailed units of geologic time. So the eon is the Phanerozoic, the era is the Paleozoic, the period is the Cambrian, and then these smaller chunks are epochs and even smaller units. The little golden spikes are just official ICS locations. It's called the golden spike. And if you want to know more about that, you can look at the ICS website and they'll tell you all about the time scale and how we know these boundaries. Let's begin by talking about what we think the geography was like during the Cambrian. And as we left off the Neoproterozoic, we had Gondwana, which was a large mass of supercratons put together in the southern hemisphere. And splitting off of that were smaller ones, but one fairly significant supercraton that rifted away from Gondwana was Laurentia. Gondwana is the dominant land mass during the Paleozoic at this time, and Laurentia was rifting away kind of on its own, and it was at or below the equator at the time. So you can see Laurentia here in Baltica and Siberia, some smaller cratonic pieces. And Gondwana is, again, the remnant of the previous supercontinent, Pannotia. The ocean, or superocean, that Laurentia is swimming in is called Panthalassa. This is the broad open ocean that dominated the northern hemisphere of the time. And the ocean in between Laurentia and Gondwana, at least in this area where Baltic is, was called Iapetus. Well, Cambrian geography is dominated by the large landmass Gondwana. This landmass, whether we want to call it a large bunch of cratons, a supercraton, a large supercraton, minor supercontinent, or even a full-blown supercontinent, is debatable. This landmass, Gondwana, included everything but Laurentia, Baltica, and Siberia. This was named by Dr. Edward Seuss in the late 19th century, and it includes all the modern-day southern continents. This grouping was used by Wegener to put forth his idea of continental drift in the early 20th century. The idea is that these continents were once together, and the idea for that came from various data like fossil evidence that showed a nice correlation between what are now widely separated continents. Just a point of fact, it was not this Dr. Seuss that named Gondwana, separate Dr. Seuss. Let's focus in a little bit more on Laurentia, the supercraton that had separated off of Gondwana. Here it is with the line of the equator for reference, showing us at or near the equator. The outline of the states shown for reference, and so Arizona is right here. Okay, and this map is from Dr. Ron Blakey at NAU, part of his series of maps that reconstruct the paleogeography of the Earth in the past. And so here's Laurentia, and remember Laurentia was once part of a larger supercontinent in the Neoproterozoic called Pannotia, and it had rifted apart from Pannotia and the rest of it, and that's how we have Gondwana and Laurentia separated now. And remember, Laurentia itself is a combination of smaller cratonic fragments, including Superior, Wyoming, Slave, these other ones. So this supercraton, if you will, is at or below the equator, and you can see in brown where we thought is a land area, and in blue where it's covered by the ocean. The lighter blue is shallow marine, and darker blue is deeper marine. And so really the shallow marine represents either where the continent is covered by shallow ocean water, or it's a continental shelf off the coast. The deep marine is probably underlain by oceanic crust. The transcontinental arch is a feature of Laurentia, and it's more or less a small mountain chain that was above sea level for a long period of time. And so it's recognizable in the rock record, and you can see it here extending down to the left. And Arizona is right at the tail end of it. So from Arizona all the way up towards Canada, extending off of the main part of the Laurentian continent, is this transcontinental arch. And I think it was a chain of maybe 6 or so areas that combined to form this highland. And around this highland were lowland areas. Here's another map showing depositional facies of the Cambrian. In white, basically where the blue line, that's the shoreline. And so all this is land, the transcontinental arch extending down towards Arizona. And then the other areas with the patterns are shallow marine areas where you're getting different sedimentary facies deposited. So you can see in yellow that's sand. The brick pattern is more carbonate, and the dash pattern is mud. Right around the arch near shore environments where mostly sand is deposited, and as you move away from that, you get more carbonate and mud. So much of the U.S. portion of Laurentia was covered by a warm equatorial sea with sand and mud and carbonate being deposited, and you had this transcontinental arch extending down to the southwest, if you will. Let's look at Laurentia in the Middle Cambrian. This is maybe about 510 million years ago. The broad landmass that is Laurentia is in brown. The shoreline extends down into Arizona. So off in eastern Arizona would have been the shoreline with Laurentia, and shallow ocean would have been present across much of Arizona, and then off to the west where California is, basically that is more open ocean. So this is all Panthalassa over here on the left. On the east coast of Laurentia, there's this broad line of islands, and that's an island arc. That's there because there's a subduction zone there where oceanic crust is being subducted under other oceanic crust, forming this line of volcanoes. And there are other continental fragments floating around there as well. This is the ocean Iapetus. This is a view of Laurentia during the late Cambrian, a few million years later. And things are pretty similar. We're still situated at or below the equator. Still have a broad, shallow marine shelf occupying much of the western part here. And off on the eastern side, you can see an encroachment by the sea inland. So shallow marine area there. And off on the eastern side in the Iapetus Ocean area there's a volcanic arc, and you can see it's a little bit closer to Laurentia than it was before. So subduction has been continuing, and this part of the oceanic crust is subducting underneath that, and it's being consumed, and the arc is getting closer and closer. One thing I like doing with these diagrams is stacking them and then looking at them in sequence very quickly, like you have a flip book. If you look at a previous image, you can see again there's that island arc, and then you look at this one, you can see how things change. For instance, the transcontinental arch isn't really defined here in this Middle Cambrian view, But then as we proceed later, the sea levels have risen or the continent has subsided, and you can see the transcontinental arch defined pretty nicely. Also, that island arc off to the right there, you can see has a certain distance at the middle Cambrian, and later in the Cambrian it has gotten closer. Let's look at the eastern part of Laurentia, and as we noted in that previous geographic map, there was a broad continental shelf surrounding much of Laurentia, and this is the model for the eastern part of the supercraton. Here's the cratonic part of Laurentia right here, and this would be the Iapetus Ocean, and here's that subduction zone I was referring to with its island arc above it. So oceanic plate subducting down underneath, another oceanic plate giving you an island arc. So we think this is the situation for Iapetus during the Middle and Late Cambrian. This is simply a little diagram showing the cross-section of a passive continental margin, meaning that there's no subduction zone here. All you have is land, and the sediments from land are being deposited offshore in a shelf, slope, and rise. That would be this part of the diagram here. So that's the passive margin of Laurentia, but farther oceanward, seaward, you have that subduction zone and island arc. There are different types of features on passive margins. Some of them are dominated by carbonate platforms, broad areas of carbonate sediments, typically in areas that are warm, shallow, equatorial waters. And so you can have a broad ramp or more of a isolated platform. There's different configurations. But you can see the dimensions here. They're tens of kilometers at least in width. As we look at western Laurentia, it's a similar situation with a broad passive continental margin extending seaward. So that ocean is Panthalassa, and the continent here is Laurentia, and there's this area of light blue, and that's the continental shelf. Here's the same diagram as on the previous slide, but it's flipped. Here's the land, here's the continental shelf sloping seaward, and then it becomes more steeply sloping as it forms the continental slope, and then finally the continental rise as it feathers out onto the oceanic crust. So we think this is the situation on the western side of Laurentia, and in fact this configuration here would be the case for several periods of geologic time until later, when the northern areas there were started to be affected by plate tectonics. Tectonics of the Cambrian, dominated by rifting and the separation of Laurentia, Baltica, and Siberia from Gondwana. Again, here's a couple views of the planet. Gondwana is this mass of southern continents here, mostly below the equator, and then a few other smaller cratons had separated off. Pannotia had rifted apart. And Baltica and Siberia, and here is Laurentia. In this diagram, Gondwana is this large continent, Siberia here, and Baltica with, it's called North America, but that's really what we're calling Laurentia. The sea in between Baltica and North America is Iapetus, and the sea on the other side in the Northern Ocean we're calling Panthalassa. The blue lines here are subduction zones, and the red lines are mid-ocean ridge spreading centers. Here are a few geologic tectonic cross-sections that span the range in time from the beginning of the Paleozoic towards the middle and end of the Paleozoic. It shows the evolution of tectonics on the eastern part of Laurentia. And so the initial rifting apart of Pannotia formed Laurentia itself separating off of Gondwana. And then you had Laurentia here on the left, separated from this island arc by the subduction zone. Oceanic crust, here's the passive margin, oceanic crust subducting underneath this other oceanic crust, giving you this island arc. And so over time, this subduction will continue, and this island arc will progressively be closer and closer to Laurentia until it finally collides later. And so you can see the evolution of tectonics on the eastern side of Laurentia in these diagrams. Let's talk about some of Laurentia's Cambrian rocks, starting with eastern Laurentia. And in this area, we see a typical transgressive sequence, a marine transgression in the rocks, where, if you remember what that is, it's a sequence where you have land sediments or even nearshore shallow marine overlain by deeper water rocks. In essence, we have sediments that were deposited at or near the shoreline, overlain by deeper water sediments as you go farther up in time. And that represents an encroachment of the ocean onto the land, a marine transgression. Okay, and these two cross sections from the early Cambrian to the late Cambrian, and here is Laurentia with the oceanic crust off to the right. Here's the passive margin where you're getting all these different sediments deposited, and then over time it's a continuation of this broad carbonate shelf, but again mostly carbonate, and the shoreline is moved farther inland, a marine transgression. Some of these carbonate rocks are fairly abundant across much of the eastern U.S., including the Elbrook Formation and the Conococheague limestone, which is shown here, a fairly typical outcrop in Virginia. Gray limestone and dolomite layers exposed in a field. Well, this diagram is a broad cross-section. You can see the map here from central Ohio into Virginia, more or less across this broad continental platform on eastern Laurentia's flanks. You can see some of these units starting in the northwest, and as you go off towards the open ocean, off across that broad continental shelf, we see a thickening of all these different units. And that thickening is because of either rapid subsidence or the water depth is increasing, we're getting more sedimentation. And so Cambrian rocks are very thick in the Virginias, and as we go to the northwest, we see kind of a thinning as you get into more shallow waters on the Craton. In the western part of Laurentia, we have rocks of similar age, and one classic unit is called the Burgess Shale. And this was deposited in the middle of the Cambrian, say around 505 million years ago, and it's a very fossil-rich unit. It's located in what is now British Columbia. Here's a map of the world at the time. Again, here's Gondwana, and here's Laurentia, and so it's on this broad continental shelf on the western side. Okay, this is what it looks like today. Okay, right up on the side of a glaciated mountainous ridge. Way up high here, these dark colored shales, it's the Burgess Shale. It's located just north of the U.S., right on the British Columbia-Alberta boundary, and it's a section of shales that are sandwiched in between carbonate rocks. And these shales are very fossiliferous, including lots of different organisms, including the first complete Anomalocaris, which is one of the earliest swimmers in the Earth's oceans. The depositional environment, we think, was shallow marine, but it could have been right on the edge of a marine cliff. And why it includes so many different organisms is proximity to this cliff, which could have been unstable, and it had a landslide event or something and buried all these animals in place, preserving them. So that's a possible depositional setting for the Burgess Shale. Also in western Laurentia, down here in Arizona, we have the Tepete Sandstone, Bright Angel Shale, and Muav Limestone, all early to middle Cambrian in age, between about 520 and 500 million years old. And these are all shallow marine sedimentary rocks, very well exposed in the Grand Canyon, and they represent deposition on this broad passive margin of Laurentia, going from nearshore marine environments to the west into deeper and deeper parts of the continental shelf. Here's a picture of the Tepete Sandstone, very resistant sandstone unit, well bedded. Above that is the Bright Angel Shale. It has kind of a greenish gray look to it, which is typical of marine shales. It's got a greenish mineral in it called glauconite. so that imparts the color to it. And then above that are more cliffy, well-bedded layers of the Muav limestone, representing a little bit deeper, clear, warm equatorial water environment. Just like on the East Coast, we saw a marine transgressive sequence where you had nearshore marine deposits overlain by deeper marine deposits. We see the same thing here in Arizona, with the Tapeats being the nearshore marine deposit and the Bright Angel and then Muav being the deeper water deposits. So they both represent the same marine transgression, both in eastern Laurentia and western. Cambrian climate, in a nutshell, it was warm. So moderately warm to very warm. These two diagrams we're going to see in succeeding lectures after this one. And the upper one shows temperature over time. So starting from the beginning of the Phanerozoic to the end right now. The bottom one is the same. It starts at the beginning of the Paleozoic and stretches all the way till the present. It shows the periods at the bottom. The upper one is a graph of temperature, and you can see how it's fluctuated over geologic time. You know that we haven't had a temperature gauge on the planet for the last 500 million years, a thermometer, but we have proxy thermometers in the rock record that indicate what the temperature might have been. And so when we correlate those together, we get a decent idea of what the temperature was like. So in the Cambrian and even into the Ordovician, we can see that it was fairly warm, what is called a hothouse in this case. The lower graph shows not temperature, but oxygen and carbon dioxide percentages. This is in ppm, parts per million, of CO2, and you can see how it has fluctuated over the Phanerozoic, and oxygen has fluctuated as well. And we're going to talk about these fluctuations and why we think they occurred and what they mean in future lectures. In essence, the carbon dioxide level of the Cambrian was very high compared to today. Today it's around 400 ppm. Back then it was several thousand. Indeed, could have been higher than 6,000 ppm, and it's been declining ever since. Oxygen on the planet was rising, as we talked about during the Proterozoic, and there were times after the Cambrian where it rose much higher. But you can see it's pretty level during the Cambrian period. Well, the Cambrian explosion of life is the main event of the Cambrian, and really it's started in the Neoproterozoic right at the very end, where we started to see complex animal life evolve. First very simple, and then it was sponges and corals, and then a sudden extreme radiation of different forms of animal life. This diagram shows the origins in the Neoproterozoic with the Ediacaran fauna here, and then across the Cambrian boundary, the extreme radiation of all these different forms. Here's the Burgess Shale layer that includes all these different types of animals. The driving factor of this is probably those ice ages that we discussed in the Neoproterozoic lecture, where at least twice the Earth was partially or totally covered by ice, which totally changed the environmental dynamic for life forms that were evolving. And from that, this radiation of new animal types, and so you can see the snowball Earth on the timeline, that period really separates a time of very simple prokaryotic and some eukaryotic organisms from much more advanced eukaryotic forms. A couple different diagrams showing the relationship of these glaciations. They probably had some role to play in this Cambrian explosion of life. Well, several fauna mark the appearance of shelled animals in the rock record. Another word for fauna is biota. These body fossils are grouped into what we call assemblages, and we can see a couple of them here in this diagram. Ediacaran fauna are one such assemblage, and they were present during the last part of the Neoproterozoic. And there were some other ones that existed as well into the Cambrian. The Timoshan fauna, for instance, was kind of the latest Proterozoic collection of body fossils that represent more complex life forms. Remember, the Ediacaran fauna was not body fossils, it was just trace fossils. These were actually body fossils about 550 million years old, and this shows some of the different forms. There are gastropods, sponges, and similar to organisms we still have on the planet. And so those are typical shelled critters of the Timoshan fauna. The Xinjiang fauna, which is early Cambrian in age, was a little younger. This is present in China, and there's a lot of different forms in this, including the recognizable trilobite. But there are other ones, including this guy right here, and that's called hallucinogenia. So there's still strange forms here which don't exist today, but many of them are recognizable today. And the Burgess fauna is one of these distinctive assemblages of fossils, marking this new explosion of life. And this is an age about 505. So these are also shown in this strat column over here, from the Ediacaran fauna down here, all the way up, showing the first appearance of, say, mollusks and brachiopods and trilobites on up towards the Burgess Shale. Well, life in the Cambrian was dominantly in the oceans. So when we're talking about marine life, we need to talk about the different parts of the ocean where it could exist. So we classify these different areas based on different things. It could be water depth. It could be the amount of light present in the water. There's different ways to do it, different terms to use. So let's just describe any life on the seafloor that lives on the seafloor as benthic. The benthic zone is that area where life is living on the seafloor. The pelagic zone is where life lives above the seafloor. And so it could be floating or swimming, different ways to do that, but it's simply living above the seafloor. The amount of light involved, if it's shallow water, we call it the photic zone, down to a depth of about 200 meters. So most of the continental shelves of today receive sunlight from the surface, and as deeper you go, that sunlight gets less and less to a certain depth, and if it's absent of any mud or anything like that, you can get a few hundred meters depth before you lose the light. So the photic zone is where you have some amount of light in the water. The aphotic zone is deeper than that. There's no light. You can have critters living in the benthic zone on the seafloor within the photic zone where they're getting light from the surface. You can have critters living on the bottom of the seafloor, thousands of meters below the surface, in the aphotic zone. So whether it's on the seafloor or above the seafloor is really what we're going to be talking about, benthic or pelagic. So let's talk about benthic invertebrates, more or less shelled critters or ones with exoskeletons. And there's a diverse array of these type of animals that are present through much of geologic time after the Cambrian. So from this Cambrian explosion of life, we see sponges, we see corals, we see bryozoans and gastropods and arthropods and cephalopods, all the typical invertebrates. Again, reading these age range diagrams, where they begin, that's the first appearance of the fossil in the rock record, and the end of it is the last appearance. Most of these go all the way through geologic time until the present, meaning that some form of the phylum is still representing on the Earth's surface today. Where they do end, that means that there was an extinction of that particular phylum. This, in case the trilobites would go extinct at the end of the Permian. So you can see the age range, but also the width of each range shows its relative abundance. The colored areas indicate where they're really widely used for correlating different rock types. So in the Cambrians, where we first see most of these different groups, some of them take a little bit longer to develop into the Ordovician. A lot of these get their start in the Cambrian, and really the trilobites, the arthropods, are the first out of the gate in terms of becoming the most abundant. That's evident by looking at the percentages of the different fossils in the Burgess Shale, and you can see that 60% or so the fossils are arthropods, and about 14% are sponges, phylum Porifera, and then the last quarter or everything else. And so the dominant phylum in the Burgess Shale is represented by critters like this trilobite, Chirus ingraicus, which is an arthropod. Another common early Cambrian benthic invertebrate are the archaeocyatha. And archaeocyathids were rooted to the seafloor, and they were filter feeders, kind of like sponges, and they would sit there and water would pass through and they would filter out the nutrients. And this is a representation of what we thought they looked like, attached to the seafloor there, and in cross section. They were very common at the time, and they've since gone extinct. Brachiopods are another important phylum that has its origins in the Cambrian, and they are still around today. And they are bivalves, two shells, rooted to the seafloor. They're benthic, and again, that's what pod means. It's foot. So pretty much there is the foot attached to the seafloor. Bivalves, each shell is symmetrical. Remember that? So when you look at a shell, you can divide it in two equal halves, so it has bilateral symmetry. It is a bivalve because it has two shells, but the one shell is larger than the other. Brachiopods, if you remember, are different from other bivalves or pelecypods, the mollusk kind, because yes, they have two shells, but the shells are different size, so they're called bivalved dissimilar. Okay, dissimilar in size, and each shell is symmetrical about a mirror plane, whereas bivalve pelecypods are bivalve similar, two shells of equal size, and each shell does not have any kind of symmetry. Brachiopods are very common in the Cambrian and later rocks. Many people's favorite benthic invertebrate are the trilobites. So these little critters were segmented arthropods. They had an exoskeleton that had 3 lobes. So it had 2 side lobes and a lobe right down the middle. So 2 pleural lobes and a medial lobe. The other way you can look at the body plan itself is that it had a head, it had a midsection, a thorax, and it had a tail or pygidium. So there are many different kinds of trilobites with many different types of heads and midsections and tails, but they all had 3 lobes. They had 2 eyes, bilateral symmetry, one from the Burgess Shale, and a recreation of what that fossil might have been doing 500 million years ago. We think most of these were crawling on the seafloor. Some of them might have taken off the seafloor, but we don't think they were swimmers. They might have come off the seafloor for a short time and then come back. But most of the record we have of them are crawling traces. And there's different ways these could have crawled along the seafloor. Many, many different kinds of trilobites. Huge diversity. This diagram shows the distribution in time of the 10 major orders of trilobites, whether it was red Leichita, Phacopoda, Leichita, etc. They had their origins in the Cambrian, and with this one order a little bit later, right at the beginning of the Ordovician. So you can see the diversity of trilobites in the Cambrian and Ordovician, and then they would all be gone by the end of the Paleozoic. You can see trilobites in the Grand Canyon. Actually, the number of body fossils of trilobites we recovered in the Grand Canyon is a lot less than you would think. It'd be only a few drawers in a stockroom, but there is plenty of signs of their activity in the terms of trace fossils. And along the Tonneau Trail, Brad here is looking at a slab of the Bright Angel Shale, which includes abundant trace fossils of trilobites. Picture on the right shows these different trails. There's my boot for scale. So trace fossils record behavior and movement, tell you what the critter was doing. While you don't have the body fossil of the animal, you do have record of its behavior, and that can be as or more powerful than the fossil itself. So these kind of traces were left as the trilobite crawled along the seafloor. They're very distinctive, and they actually have a name called Cruziana. If the trilobite lifted its exoskeleton off the seafloor and skittered its way across the sand, it would leave a slightly different trace, and that has a name. And if it sat down in one place along its walk and burrowed into the sand, it would leave a slightly different pattern, and that actually has a name. So all these are different types of trace fossils of the same organism, a trilobite. A little high quality animated GIF there for you. Pelagic invertebrates. What are we talking about here? Pelagic means living above the seafloor, and invertebrate means doesn't have a spine, it's a shell or a exoskeleton. Must be talking about Anomalocaris. Okay, so this is one of the main pelagic arthropods of the Cambrian. It was mobile and it was a swimmer. There weren't any fish at the time, so Anomalocaris would have had the seas to itself. You can see this is what it looked like. It had 2 eye stalks, tentacles in front. See the relative size compared to a human, and it was mobile. You can see these fossils from the Burgess Shale. Would have been a trilobite's worst nightmare. So Anomalocaris is kind of the super predator of the Cambrian seas. Pelagic chordates. So these are animals that are part of phylum Chordata, and Pikaia is a very famous representative of these. And these are very primitive and early formed chordates. We are part of phylum Chordata. These are not vertebrates because there's no spinal column yet, but there is a nerve cord. This nerve cord, called a notochord, stretches from one end to the other, and that is a distinct characteristic of phylum Chordata animals. These animals would soon develop a structure to support the notochord, and then they would become vertebrates. So we think these were pelagic as well, just like Anomalocaris. Much smaller in size. You can see the actual size here compared to a person, so very small. But they were important nonetheless, because these are the first members of our phylum really to exist in any kind of abundance. Sometimes it's hard to decide what the head and tail is, but they did have a head and a tail. They had bilateral symmetry and all that. But these were the first real chordate swimmers. Now the Ordovician period, 485 to 444 is its range. Here's the ICS timeline showing the Ordovician. 485.4 down to 443.8. That's the Ordovician. There's an early, middle, and late, or lower, middle, and upper, if you will. This period was named after the Ordovics, which were a Roman area Celtic tribe in an area near Wales. So similar to the Cambrian rocks, Ordovician rocks were first studied in the same part of the world. Here's an angry Ordovic right there. Close up on the geology of this area. Again, Wales is up here. The Ordovic area is down here. So rocks of Cambrian and Ordovician age exposed in this part of England. The geography of the Ordovician was very similar to that of the Cambrian. And where we left off from last time, we had Gondwana occupying much of the southern hemisphere and a few other scattered cratons to the west, whether it was Baltica or Siberia. Laurentia was the biggest one. Panthalassa was the major ocean off in the northern hemisphere and off to the west. Iapetus is the ocean between Laurentia and Baltica and areas south. And the Paleotethys Ocean was off to the east, more or less between Laurentia and Gondwana. We think sea levels were actually higher during this time. Temperatures were higher during the Cambrian. That would extend into the Ordovician. So that would probably mean very little ice, surface ice on the planet. Sea levels were probably higher. That means that we had marine transgressions pushing sea levels up onto continents and the shorelines moving inland. And so this would continue until the late Ordovician before there was any real change. Let's focus in on the geography of Laurentia during the Ordovician. And just like the Cambrian, much of Laurentia was covered by warm, shallow seas. You can see here the area above sea level, and much of the southern portion in this map view with the light blue, that's the continent itself covered by shallow seas. Here's another map showing Laurentia and where the equator is. This is where Laurentia is above sea level off to the north. Off to the west, this is the volcanic arc that I had mentioned before off to the west, and so there's a subduction zone there and a line of volcanoes and an island arc, and that's been slowly approaching Laurentia from the west. That's going to be a geologic story of the near future that we'll talk about. Much of Laurentia here is inundated by warm, shallow seas with deposition of muds and carbonates. The transcontinental arch is still a feature. Parts of it are totally submerged, but other parts are still emergent, sticking up above sea level, and the largest part we think was down near Arizona. We think this because there's very little in the way of Ordovician rocks in Arizona. We think it was mostly above sea level for much of the Ordovician. Off on the east coast, very active tectonics would create what are called the Taconic Mountains or the Taconic Highlands, and this is the result of a orogeny we call the Taconic orogeny, which we'll discuss in a minute. Okay, here are a series of maps, starting with the early Ordovician, 485, showing Laurentia and the transcontinental arch and the southwestern end where New Mexico and Arizona are still above sea level, with the shallow continental margin, shallow marine continental margin extending around like this. Here is the volcanic arc on the east coast, and then a little bit later at about 470 in the middle Ordovician, you can see that arc starts to collide in the northern part of Laurentia, and eventually it will work its way south, this collision. Much of the central part of the craton again remains warm, shallow seas, transcontinental arch largely submerged except for a few parts including Arizona. And then in the late Ordovician, the culmination of this merging of the island arc on the east side with Laurentia, but a continuation of warm, shallow sea sediment deposition across most of the craton. So if we go through the flip book here, you can see how things changed during the Ordovician. So let's look at the transcontinental arch right here. Let's look at the northern part. And then let's look at how this island arc works its way to the west and contacts Laurentia. One final thing to note, guy over here getting ready to make its way west towards Laurentia, that's something that we'll talk about soon as well. Well, in eastern Laurentia, the Ordovician started as a continuation of the Cambrian with a broad continental shelf, warm shallow seas extending off to the east and southeast towards the open ocean. But that would change in the later part of the Ordovician as that island arc would come closer and closer and finally collide with Laurentia, and that mountain building event would form a line of mountains called the Taconic Highlands. And once they're above sea level, they'll begin to weather and erode and deposit sediment along their margins, and you get broad coastal plains on either side, but huge debris fans and coastal plains present off the west side of this Taconic Highlands area onto the Laurentian craton. This is a cross section of the tectonics of the Taconic Highlands, showing how this island arc sequence got thrust up and onto the edge of Laurentia, and then these mountains were formed, and those mountains would create sediment which was deposited off to the west. As far as western Laurentia goes, a little different situation. Still a passive margin here with shallow marine environments extending around much of it. The transcontinental arch was present though, and Arizona was mostly above sea level during the Ordovician. So transcontinental arch still present in the southwest area. Very few Ordovician rocks to represent deposition like this. Broad, open, shallow marine environment extending from the shoreline off towards the deeper ocean. So this is possibly what much of the western part of Laurentia looked like during the Ordovician. Very little on the land, but a nice passive shallow marine margin on the western part. right at the west end of the transcontinental arch. Let's talk about tectonics of the Ordovician. Really at the end of the Ordovician, on the eastern side of Laurentia, we had the tectonic orogeny. This was the collision of that island arc sequence off to the east with Laurentia. Finally, this has happened. That broad carbonate platform on the passive margin of Laurentia was destroyed as this island arc sequence was thrust up onto the shoulder of Laurentia. This is the first of 3 major mountain building events in the formation of the Appalachian Mountains themselves. As we started Cambrian, there was Laurentia here, and then a subduction zone off to the east and southeast with an island arc developed above it. Then in the Ordovician, with progressive subduction of this oceanic crust, this island arc finally collided with Laurentia. This is the tectonic orogeny. This was the first mountain building event. It formed the Tectonic Highlands, and there will be a couple others that we'll talk about soon. One being the Acadian orogeny, which involves Avalonia here and its collision with Laurentia, and then the big one where Gondwana, represented by Africa, colliding in the big culminating continent-continent collision. Tectonic orogeny, named after the Tectonic Mountains in New York. Let's talk about some Ordovician rocks of eastern Laurentia. And looking at this strat column over here, we can see the Cambrian rocks, mostly carbonates, representing deposition on that broad carbonate platform on the passive margin on the eastern side of Laurentia. And that continues into the Ordovician through much of this area here on the eastern side of Laurentia, still dominantly carbonate deposition. And then at the end of the Ordovician, we start to see more clastic sediments, muds, and sands, which represent the appearance of the Tectonic Highlands, shedding more clastic sediment. Right here is the Chapultepec limestone. It's a early or lower Ordovician limestone present in southwestern Virginia. This is Natural Bridge. The Natural Bridge is simply an arch with water flowing underneath it. Very distinctive little park in southwestern Virginia. Younger Ordovician rocks, the strat column shows where they are located here. The Edinburgh Formation, the Martinsburg Formation. Those earlier carbonate rocks are now progressively giving way to more clastic rocks, muds, and sands. And the reason for that is the appearance of the Tectonic Highlands. And these highlands would then weather and erode and shed sediment off to the west into this large depositional basin here. And there was a broad coastal plain and deltas where all these muds and sands were deposited, both stream-related fluvial sediments and shallow marine sediments. So it's a huge wedge of sediment we call a clastic wedge, all from the erosion of these tectonic mountains. Before we talk about Ordovician life, let's look at the climate we think existed during the Ordovician. More or less an extension of the Cambrian for the most part, very warm. You can see the temperatures through the Cambrian and Ordovician were very warm, hothouse kind of conditions. And then at the very end of the Ordovicians, things would change drastically. So we think that represents an ice age. And the reasons for that could be several. One could be Gondwana moving more to a position centered on the South Pole, allowing ice to build up there more easily. The reduction in CO2 since the Cambrian by several thousand ppm might have weakened the greenhouse effect to some degree. And there could have been other factors as well. And so at the end of the Ordovician, the climate was much different than the early and middle part. Life in the Ordovician is dominantly invertebrate in terms of animal life. Diverse suite of all our old friends, benthic animals, mostly with a few swimmers. On the left shows all the different types of invertebrates, whether they're bivalve mollusks, brachiopods, echinoderms, trilobites, straight cephalopods called nautiloids, corals, crinoids. Okay, here's a depiction of these straight cephalopods called nautiloids That's Orthoceras. And we think this was probably the largest pelagic predator in the Ordovician seas. So this Orthoceras would have been the super predator of the Ordovician. See these trilobites down here scurrying on the seafloor. Ooh, and there's a sea scorpion, a Eurypterid. Very scary. These are crinoids. Well, now we can talk about pelagic vertebrates. Okay, and these include the first fish. They were jawless, and most of them were armored. Many different kinds, 10 families of these different jawless fish, commonly called ostracoderms, jawless fish, and there are many different variations, but they all lacked a jaw. They had some kind of orifice to input the food, no jaw. Lots of different weird variations. These jawless fish were radiating from the Ordovician, and they would continue for a while, and then most of them will die off and go extinct. There are a few related forms that are still present today, but these would evolve into, of course, jawed fish with time. They did have gills that they developed for respiration, and it was the development of gills that eventually led to the jaw structure itself. So from Pikaia, the earliest chordate, fish developed a support structure, a spinal column to support that notochord, and we have the first vertebrates. So Pikaia, our oldest chordate ancestor, and then the jawless fish, the ostracoderms, would give way to jawed fish and will progress along this chordate vertebrate family tree. Let's finish our discussion of life forms talking about Ordovician plants and land plants. For the first time, plants are evolving onto land, and these are very primitive, non-vascular plants that would be the first ones to inhabit land areas. This is an example of a typical non-vascular plant today, encrusting rocks like that. And most of these were what we call spore plants, meaning that they would need a watery environment to procreate, and places like this, a river, marsh, estuary environment, is where spore plants typically flourish. So it would be an area like this, which would be where we'd find most of our plant life during the Ordovician. And to end the Ordovician, just like there was a change in the climate, there was a change in life on the planet in the form of a mass extinction. And the Ordovician will end with the first large mass extinction of the Phanerozoic eon. In fact, it's the second largest mass extinction of all time. This graph here shows geologic time from the Cambrian to Ordovician all the way to the present day from right to left. You can see a steady increase from the Cambrian up to the end of the Ordovician, and then a relatively large drop. So that is the end of Ordovician mass extinction. The first of 5, and notice these 5 yellow triangles, what are called the big 5 mass extinctions of the Phanerozoic eon. The Ordovician was one of these, and its cause, we think, was glacial. Nothing spectacular, just plate tectonic movement where Gondwana, not necessarily centered on the South Pole, but enough of that land mass was at a high enough latitude where ice could build up and stay. And so the accumulation of ice over time led to change in the climate, plus any other factors that might have been present, like orbital conditions, orbital changes. Can't really pin anything like that down, but this glaciation, the end of the Ordovician, was a major one. This diagram shows the Neoproterozoic snowball Earth glaciations, where we think that from the equator all the way to the poles was covered by ice. The third one of the Neoproterozoic, not quite as significant in length or extent, and most of the ones after that might have been long in terms of timing, but they didn't approach snowball Earth conditions, probably only covering a few tens of degrees of latitude on the planet, but still enough to change the climate. And so this was one that happened right at the end of the Ordovician. And if you think about it, what happens during a glaciation? The water gets tied up in the ice, sea levels drop, And all those shallow marine areas full of all that life is exposed to the atmosphere. Now, if those benthic organisms can move and follow the sea as it recedes out, then they're okay. But anything tied to the seafloor is gonzo. And so the swimmers probably didn't have as much of a problem, but many of these organisms did. And the food chain gets disrupted, and it led to a mass extinction where we think that 85% of those marine species went extinct at the end of the Ordovician. So this shows at low tide, all these organisms are exposed. Of course, tide will come up, then they're covered again, but you can think of this glaciation as a low tide that doesn't come back. So all these life forms are exposed and left to die, and that's how we end the Ordovician.